All right, so we're going to look in 8.1 at what's called inverse variation, and we're also going to look at like the constant of variation and joint variation and direct variation and all this different types of variation. So with two variables with inverse variation, two variables x and y show inverse variation if they are related as follows. And then we've got a little formula here: y equals some constant over x. And if you've got y equals some constant over x, where x is down in the denominator, and that a cannot be equal to 0, you have what's called inverse variation. So the constant a, this a guy right here, is called the constant of variation. And you will have him every time you have inverse variation. It's easy to forget him, but he's always there. Now, just as a quick reminder, we've seen direct variation, and it looks like the slope part of an equation, y equals mx, where the x is in the numerator. That's direct. So if x is in the denominator, down, it's inverse. Okay? So just a few things here. Tell whether x and y show direct variation, inverse variation, or neither. And notice that on this first guy right here, we've got x times y equals 7. So let's go ahead and solve that bad boy for y. So you're just going to divide both sides by the x. Divide both sides by x. So what you end up with is y equals 7 over x. This is exactly like what we just talked about in the setup. Okay, this is inverse variation. Okay, inverse variation. And oh, by the way, you'll need to know the constant of variation is that number on top of the x. It's a 7. All right, look at part B. Part B says y equals x plus 3. Well, this doesn't have the x in the denominator, and it just doesn't have x all by itself with a constant. So this guy right here, this middle guy, is neither. All right, well, what about the last guy? It says y over 4 equals x. Well, again, get that y all by itself, and in order to do that, you're going to multiply both sides by 4. So when you multiply this by 4, when you multiply this by 4, what you end up with is y equals 4x. And hey, that looks an awful lot like direct variation. So that is what it is. And so these are some different types of variation that you can have. They're not hard to recognize, and they're not hard to set up when they're kind of in this simpler form like that. But they can get tricky. So remember, inverse, you've got a number over x, and direct, you have a number times x. Okay, so the variables x and y vary inversely, and what we're saying is that y equals a over x. That's the relationship. And then they tell us y equals 7 when x equals 4. In other words, 7 equals a over 4. So a is 28. All right, and how did we get that? Well, you just multiply both sides by 4. So times 4 here and times 4 here. Okay, so the equation this guy right here, this 28, is my constant of variation. And so what my equation really is y equals 28 over x. This is the equation I'm actually going to work with. So then the next part of the problem that we're asked to solve is write an equation that relates x and y. We just did that. Then find y when x is 2. So now taking this new equation right here, we're going to let x equal negative 2. So what have you got? Y equals 28 divided by negative 2, which is negative 14. Okay, now a story problem which kind of relates all of this together and lets us see how it's going to work. The number of songs that can be stored on an MP3 player, think iPod, player, varies inversely with the average size of a song. So a certain MP3 player can store 25,000 songs when the average size of the song is 4 megabytes. Did you catch that? We've got our variation right there. The number of songs that can be stored on an MP3 player varies inversely with the average size. So think about it this way. N, the number of songs, equals the constant of variation, A, over the size, S, of the song. Okay, so N is the number of songs. S is the size of the song, and A is your constant of variation. And if you'll label these things what they are, the problems aren't quite as challenging to solve. So then they tell us, hey, 25,000 songs when the average size is 4 megabytes. There's your number. There's your S for size. So we're actually going to work out the problem then where 25,000, it's a comma, 25,000 is equal to A over 4. So this is going to give me then my coefficient, my correlation, well, not my correlation, coefficient, my constant of variation. So multiply both sides by 4 and you get 100,000 is equal to A. So for this particular problem, the equation that I'm looking at, my model is N equals 100,000 divided by the size. Okay, so write a model that gives the number of N songs. Here's my model. Now, make a table showing the number of songs that will fit on an MP3 player if the average size of a song is 2, 2.5, 3, and 5. And what happens is the average size of the song increases. So if I look at the size of the song, S, so I'm going to look at this as the size of the song. And then down here on the bottom, we're going to have the number of songs that will fit. And they want us to know when S is 2, when S is 2.5, when S is 3, and when S is 5. So we're just basically, you're going to put all these guys right here in for the S down here, okay? And you're going to figure out a number. So when you put 2 in for S, you get 50,000. That won't fit in my little space here. So this first guy is 50,000 songs. And then when I put 2.5 in, that's not going to fit either, but 100,000 divided by 2.5 is 40,000. And then 100,000 divided by 3 is 33,333. And then 100,000 divided by 5 is 20,000. So the question is, what happens as the average song size increases? When the average song size increases, the number of songs on the MP3 player decreases. And that's how you look at inverse variation in real life. And if you think about it, that's what you're doing every time you hook your iPod up to your computer and sync your songs to it. Okay, another little word problem here. The table compares the area in square millimeters of a computer chip with the number C of chips that can be obtained from a silicone wafer. So write a model that gives C as a function of A, and then predict the number of chips per wafer when the area of a chip is 81 square millimeters. So we've got this table here, and we want to figure out a model that's going to work. And so it says the area of a computer chip. Okay, so we're looking at area, which is the top row. Okay, that can be obtained from a silicone wafer. You can get this many chips from it. Okay, so what we're looking at is the area times the number of chips. Okay, so this first guy then is just going to simply be 58 times 448. That's the very first one we're looking at. Again, we're looking at the number of chips we can get from that area. Okay, so if we've got 58 square millimeters, we can get 448 chips. So when you multiply those two guys together, you end up with 25,984. Okay, then when I have an area that's 62, I get 424 chips. Okay? So again, we're comparing the area in square millimeters of a computer chip with the number of chips that can be made. So when my model gets bigger now, so my area of my chip gets bigger, then from my silicon, I get less chips. Okay? And so that's going to be 62 times 424, which is 26,288. And then if I look at the next guy, the area of my chip grows again. In my silicon wafer, the size is not changing, so the number of chips I can get it's decreasing each time, is now going to be 25,872. And then what's happening here? I've got an area of 70 and my number of chips decreases again, so when I multiply those two guys out, I end up with 26,320. All right? And so if you look at all of these guys, there's not a lot of difference in all these numbers. All these numbers are really close. If you round just a little bit, they're all really close to 26,000. Okay? And so what we've got is when you can take two parts of your table, like basically your x numbers and the y numbers, and you multiply them together, that shows inverse variation. Remember, inverse variation says y equals a over x. And so if I multiply both sides by x, then what I end up with is x times y equals a. And in this case, when I do that, when I multiply the x with the y, I get about 26,000 every single time. Okay, so what model does my inverse variation look like? Well, it looks like y equals, my model for this is y equals 26,000 divided by x. Well, what is y? Y is the number of chips. What is x? X is the area of each chip. So the question then is, the number of chips per wafer when the area of the chip is 81. So now what am I going to do? I'm just going to take my 26,000 and divide it by 81. And when I do that, I'm going to get the area as the number of chips. And so that area is going to be 321, about 321. It'll be really close. So that's another way that you can find inverse variation. Okay, so joint variation occurs when a quantity varies directly with the product of two or more other quantities. So joint variation can be challenging. In the equations below, A is a non-zero constant, so that A is still around. We have to know what A is, and he's at the front of both of these equations. But these show joint variation. Okay, Z varies jointly with X and Y. P varies jointly with Q, R, and S. Okay, so joint variation can be tricky, and it's going to take a little bit of practice to catch what the pattern is. All right, so the variable z varies jointly with x and y. So this guy right here matches up perfectly with my very top row. So what's my equation going to look like that I'm going to work with? Z equals axy. Then it tells me z is negative 75 when x is 3 and y is negative 5. So the only variable I don't have is a, so I can plug all these guys in and solve for a. And what I end up with is negative 75 equals negative 15. A, divide everything by negative 15, and you get a equals 5. Okay, so my model then that I'm looking at is going to be z equals 5xy. And then they give me a rule when x is 2 and y is 6. So now I just plug 2 in for x, 2 in for x, and 6 in for y. And when I do that, I end up with z equal 10 times 6, or z equal 60. So again, it's not a long drawn out horrible process. You're going to work each problem twice, go one step at a time, and you should be fine. Okay, and lastly, just some practice. Looking at all the different types of variation that we've looked at in this section. So what we're going to do is we're just going to rewrite all these guys with different in different ways. Okay, so y varies inversely with x. Go back through your notes, find an example. You're going to see that it looks like this: y equals a over x. Z varies jointly with x, y, and r. And remember, joint we just looked at, so z varies jointly. And don't forget, you need that constant of variation every time. That a has to be written down first every time. It's always in the numerator. So x, y, and r are the variables. Y varies inversely with the square of x. So again, inverse is going to be a over x, but x what? Squared. Okay. Z varies directly with y, so z varies directly with y and inversely with x. It's going to look like this. And lastly, x varies jointly with t and r, so a, my constant of variation, t and r, and inversely with s, like this. So it just takes a little practice. If you can do these problems right here, these are about as tricky as it's going to get with your variation. If you can set these guys up, every time, and it just takes some practice, then variation problems will get a lot easier.